Hello, and welcome to the Chemistry Solution. This tutorial is on weak acid equilibria. This tutorial specifically covers weak acid equilibria, so if you are looking for help with other types of equilibrium problems, check out some of the other tutorials on my channel. To start out, I wanted to review the difference between strong acids and weak acids. So when we think about strong acids, what makes something a strong acid is that it's going to ionize completely in solution. So if you had hydrochloric acid, it will ionize completely in solution to give you your hydrogen ions and your chloride ions. If you were to look at an acid like nitric acid, which contains the polyatomic ion nitrate, it will also ionize completely into hydrogen ions and then your nitrate ion. The difference then with a weak acid is that your weak acids are going to dissolve completely but only partially ionize in solution. And so typically we represent what is happening with weak acids in solution using our double-sided arrows to represent equilibrium. And you can see with hydrofluoric acid here, which is a weak acid, it will ionize to some small extent to give you some hydrogen ions and some fluoride ions in solution. You can also have weak acids that contain polyatomic ions. And so here we have acetic acid, also ionizing partially in solution to give you hydrogen ions and acetate ions. When we consider which acids are strong acids, there are relatively few strong acids. Depending on the reference text you use, you're looking at about 7 common strong acids. We're going to focus on weak acids for the rest of this tutorial. Before we start looking at some calculations involving weak acid equilibria, I want to review 2 different ways that we can write out our aqueous acid dissociation or ionization reactions. You can write out these reactions completely, where you show your weak acid, your Bronsted-Lowry acid, acting as your proton donor, and in this scenario, water acting as your base, your proton acceptor, giving us our hydronium ion and our fluoride ion here. This is the most technically correct way to write out the reaction of this weak acid in water. But we can also write out this acid dissociation or ionization reaction in a simplified version where we leave out water, where we just show our weak acid ionizing partially in solution to give us our hydrogen ions and our fluoride ions. And for this tutorial, I'm going to write out these reactions using this simplified version. And so when you look at the ionization or dissociation reactions of these weak acids in solution, you're going to start to notice a pattern. And so we can represent this ionization of our weak acids in solution using this general formula, where HA represents our weak acid, and it ionizes to some small extent in solution to give you H plus and A minus, which is going to represent the conjugate base of your weak acid. So if I was looking at this reaction of hydrofluoric acid in solution, hydrofluoric acid could be represented as HA, and then F minus, the conjugate base of hydrofluoric acid, would be represented as A minus. We can also do this with weak acids that have more complicated formulas. So if I were to look at acetic acid, we can represent the entire formula for acetic acid as HA, and then it's going to ionize in solution to give you H plus and your acetate ion, which is the conjugate base of acetic acid, and we can represent that as A minus. And so taking this general reaction for our weak acids in solution, we can write an equilibrium constant expression for this reaction. Our equilibrium constant expression is going to be written the same way that we write all of our equilibrium constant expressions, with the concentration of products over the concentration of reactants, all raised to the power of their stoichiometric coefficients. In this case, the stoichiometric coefficients are all 1 to 1, and all of our reactants and products are aqueous, so they are all going to be included in this equilibrium constant expression. And we give this equilibrium constant a special designation. We call this Ka, where Ka is our acid dissociation constant. We're looking at the extent to which this weak acid is going to ionize in solution when equilibrium is established. And so when we think about the significance of Ka and the information that it provides, the larger the value of Ka, the stronger the acid. And so in chemistry, we've defined weak acids as being those acids that ionize only partially in solution. But the extent to which these weak acids ionize can still vary among acids that we consider weak. So let's consider 2 scenarios here. So here we have hydrofluoric acid, if I were to write the equilibrium constant expression for hydrofluoric acid, it's going to be equal to the concentration of our hydrogen ions multiplied by the concentration of our fluoride ions divided by the concentration of hydrofluoric acid that exists in its molecular form. And so when we think about this value of Ka, the larger the value of Ka, the higher those concentrations of H plus and F minus are going to be relative to the concentration of our acid in its molecular form. And if you were to look up the value for Ka for hydrofluoric acid at standard temperature, you're going to see that the value of Ka is 7.2 times 10 to the negative fourth. Knowing what we know about equilibrium constants, this value for our equilibrium constant is still very, very small. It still indicates that most of this acid is going to exist in the unionized form, and it's going to only ionize to a small extent in solution. We can also compare this to the Ka value for acetic acid. Note that we're going to write this equilibrium constant expression the same way, and both of these equilibrium constant expressions follow this general expression that we've written for Ka for a weak acid, and the value of Ka for acetic acid is 1.8 times 10 to the negative fifth. So even slightly smaller than the Ka value for hydrofluoric acid, meaning that if you were to compare these two acids in solution, hydrofluoric acid is going to ionize slightly more in solution than acetic acid would. So let's get into some examples involving weak acid equilibria. And let's start by calculating Ka if we're given some experimental data. So here we have dissolved 0.1 moles of hypochlorous acid in 1 liter of solution. Equilibrium has been established, and the pH of this solution is measured to be 4.26 at 25 degrees Celsius. Let's calculate Ka for hypochlorous acid at this temperature. So we can write out the acid dissociation reaction using the formula of the acid, or we can use our generic expression where we abbreviate the weak acid as Ha, where H plus is our ionizable proton and A minus is the conjugate base of the weak acid, in this case, the hypochlorite ion. So our first step is going to be writing out the acid dissociation reaction. You can write out this reaction using the full formula of your acid, or you can use the general expression where you represent your acid as Ha and the conjugate base as A minus. The next thing we're going to do is we are going to set up a chart that I've labeled ICE, where I stands for initial, C stands for change, and E stands for equilibrium. And then we want to start filling in the information that we know. So in this scenario, 0.1 moles of hypochlorous acid was dissolved in 1 liter of solution. And so our initial concentration of our weak acid is going to be 0.1 molar. So this is our concentration in moles per liter. Our initial concentration of A minus, or our conjugate base, in this case the hypochlorite ion, is going to initially be 0. And when we consider the initial concentration of H plus, here's where we're going to make an assumption. We're going to make the assumption the initial hydrogen ion concentration is 0. That's not technically true. We know that the hydrogen ion concentration in pure water is 1 times 10 to the negative 7th molar, assuming we're at 25 degrees Celsius. This is due to the autoionization of water. But this value is going to be much smaller than the concentration of H plus that is going to result from our acid dissociation. And so to simplify these types of problems, we are going to assume that this is a negligible amount, and we are going to fill in our initial hydrogen ion concentration as being equal to 0 molar. We now want to consider how these concentrations are going to change as we reach equilibrium. So we know that in order to solve for Ka, we need the concentrations of all of our reactants and products at equilibrium. Right now we have the initial concentrations. So how are these concentrations going to change as equilibrium is established? Well, I know my weak acid Ha is going to ionize to some small extent in solution. This concentration is going to decrease. I don't know the exact amount by which it will decrease, so I'm just going to put in this column here for C that the concentration of my weak acid is going to decrease by some currently unknown amount, which we'll call X. It's going to decrease by X. Now, based on the stoichiometry of this reaction, where we have 1 to 1 to 1 stoichiometric coefficients, If HA, our weak acid, decreases by some amount X, then the concentrations of H plus and A minus are both going to increase by that same amount. So I'm going to put the change for H plus and A minus as being equal to plus X. And again, this goes back to the stoichiometry of the reaction. For every molecule of your weak acid that ionizes in solution, you'll get one H plus and one A minus. The other piece of information that we have in this problem is that the pH of this solution at equilibrium is 4.26. Now we know that if you know the pH of a solution, you can calculate the concentration of hydrogen ions in solution. And so knowing that the pH is equal to the opposite of the log of the hydrogen ion concentration, you can rearrange this equation to solve for your hydrogen ion concentration, which is going to be equal to 10 raised to the power of the negative pH. And so if we take 10 raised to the negative 4.26 power, what we'll find is that our hydrogen ion concentration is 5.5 times 10 to the negative fifth molar. This is going to be the hydrogen ion concentration at equilibrium. And so this provides some interesting information with respect to the value of X. So we know that our initial hydrogen ion concentration was 0 molar. And again, this was an approximation, but the hydrogen ion concentration in pure water is small enough to be considered negligible for these types of problems. And we know that our hydrogen ion concentration at equilibrium is equal to 5.5 times 10 to the negative fifth molar. And we calculated this based on the pH of our solution at equilibrium. So the concentration of my hydrogen ion increased from 0 to 5.5 times 10 to the negative fifth molar. Now, the way that we've defined these changes of concentrations of reactants and products in terms of X, if I went from 0 to 5.5 times 10 to the negative fifth molar, that change is equal to X. And so if my hydrogen ion concentration increased from 0 to 5.5 times 10 to the negative fifth molar, then the concentration of my conjugate base also increased from 0 to 5.5 times 10 to the negative fifth molar. This is also going to tell me that the concentration of my weak acid is going to decrease by 5.5 times 10 to the negative fifth molar. Now we can go ahead and do that calculation. We can take 0.1 minus 5.5 times 10 to the negative fifth molar. And if you were to put this into your calculator, you would get a value of 0.099945 molar. But thinking back to significant figures, when we're performing the operation of subtraction, the number of significant figures that we keep is the same as the value with the least number of digits past the decimal point. So we are limited here by our initial measurement of 0.10 moles of hypochlorous acid. So if I were to do this calculation and keep track of significant figures, what you're going to see is that we would need to report our value to the hundredths place. And you can see that this is going to round to 0.10 molar. And this is going to be an important thing to keep in mind as we consider additional weak acid equilibria calculations. So now that we know the concentrations of our reactants and products at equilibria, we can now plug these into our equilibrium constant expression, and then you can plug this into your calculator, and what you will find is that the Ka for hypochlorous acid is 3 times 10 to the negative eighth. And when we think about comparing this value to some of the other examples we've looked at in this tutorial, hydrofluoric acid and acetic acid, what you'll notice is that this Ka value is even smaller. That's going to indicate that hypochlorous acid is even a weaker weak acid than hydrofluoric acid or acetic acid. Okay, let's go through one more calculation involving weak acid equilibria. Let's calculate the pH of a solution prepared by dissolving 0.1 moles of acetic acid in 1 liter of solution if we know that the Ka for acetic acid is 1.8 times 10 to the negative fifth. We are going to start out this problem the same way. We're going to write out our acid dissociation reaction. Again, you can write out this reaction using the complete formula of your weak acid and its conjugate base, or you can write out the general reaction for a weak acid. And then we are going to follow this by setting up an initial change equilibrium chart. and we'll start filling in the information that we have. So we know that our initial concentration of our weak acid is 0.1 molar. In this scenario, we have 0.1 moles of acetic acid in 1 liter of our solution. So we get a concentration of 0.1 moles per liter, or 0.1 molar. Again, we're going to assume that our initial concentration of H plus is 0. And we know that the initial concentration of our conjugate base, represented here as A minus, is also 0. And then we'll consider how these concentrations are going to change as equilibrium is established. We know that some of our weak acid is going to ionize in solution, so the concentration is going to decrease by some amount. Again, we don't know what that amount is here, so we're going to call that amount X. And we'll say that the concentration of HA will change by some amount minus X. Based on the stoichiometry of our reaction, if HA decreases by some amount X, the concentration of H plus and A minus will both increase by that same amount. So the change in the concentration of H plus and A minus will both be equal to plus that same amount X. So in this scenario, we're not given the equilibrium concentrations of any of our reactants or products. We're not given the pH of the solution. That's actually what we're trying to find. So I want to find the concentration of H plus at equilibrium in order to calculate the pH. So we're going to fill in the equilibrium concentrations in this chart in terms here of X. So the concentration of my weak acid initially was 0.1 molar. It decreased by some amount X. And so I would say at equilibrium, the concentration is going to be equal to 0.1 minus X. The concentrations of both H plus and A minus were initially 0. They increased by some amount X, and so the equilibrium concentration of both H plus and A minus are going to be equal to X and equal to each other. And this leads us to the next assumption that we're going to make with these types of problems. So if the value of Ka for a weak acid is very small, typically on the order of 10 to the negative fifth or smaller, you can assume that the amount of dissociation is negligible with regard to the initial acid concentration. And so here we said that our weak acid is going to ionize to some small extent in solution. So this concentration of 0.1 molar is going to decrease by some amount X. But we also know that HA is a very weak acid. The Ka value for this weak acid is 1.8 times 10 to the negative fifth. And so this change, this decrease in the concentration of our acid in its molecular form is going to be very, very small. Small enough that when you subtract it from 0.1 molar, you're still going to be left with about 0.1 molar. And that's the exact scenario that we saw in the last example, where in particular, if you are keeping track of significant figures, it's not going to change that initial value with respect to significant figures. And so we can say that our concentration of our weak acid at equilibria is still going to be about 0.1 molar. Now, when we think about the concentrations of H plus and A minus at equilibria, here we went from 0 to something. So that's still going to be significant. But when we're subtracting X from 0.1 molar, that's not going to significantly change that initial concentration because so little of this weak acid is actually going to ionize in solution. Okay, in this scenario, we have the value of Ka, and we have some equilibrium concentrations for all of our reactants and products, even though they're still in terms of X. But because of this approximation that we were able to make, where the concentration of our weak acid is decreasing by such a small amount that the equilibrium concentration is still effectively the same, 0.1 molar, that is going to simplify our math quite a bit. The last thing I'll note here is that if you don't want to make this approximation, if you don't want to make the approximation that X is so small that when you subtract it from this initial concentration of your weak acid, it doesn't substantially change the value, you don't have to do that. You can plug in your equilibrium concentration for your weak acid as 0.1 minus X. You're going to just put that value in here in your equilibrium constant expression, 0.1 minus X, and you can still solve this mathematically. you would just need to use the quadratic equation. Now you should come up with essentially the same answer, especially with respect to significant figures. But if you are looking for an additional challenge, go ahead and try that out. Plug in 0.1 minus x here, use the quadratic equation to solve for x, and see if you get the same answer that I do at the end of this problem. So we can plug our equilibrium concentrations here into our equilibrium constant expression. We have x times x on the top, which is going to be equal to x squared. Now we can go through and multiply each side of our equation by 0.1, and then we can take the square root of each side, and what we're going to find is that x is equal to 1.34 times 10 to the negative third molar. Now we know that the concentration of H plus at equilibrium is equal to x, and we also know that in order to solve for the pH, we need to know our hydrogen ion concentration. And so we can solve for the pH by taking the opposite of the log of our hydrogen ion concentration. And if you do that, you should come up with a pH that is equal to 2.87. Thanks for watching. I hope this was helpful.